Welcome! In this session, we'll explore an intriguing problem titled Minimize Rounding Error to Meet Target. This problem challenges us to work with rounding strategies to meet constraints, requiring a mix of mathematical intuition and algorithmic precision. Let's dive in. In this problem, we are given a list of prices as strings and a target integer. The goal is to round each price either down to its floor value or up to its ceiling value such that the sum of all the rounded prices equals the target. At the same time, we need to minimize the overall rounding error, which is defined as the absolute difference between the original price and its rounded value. For example, if a price x is rounded down to its floor, the rounding error is the difference between x and its floor. Similarly, if it is rounded up to its ceiling, the rounding error is the difference between the ceiling value and x. If achieving the target is not possible, we should return -1. The result should be returned as a string, formatted to 3 decimal places. To clarify the output format, the result is a string representing the minimum rounding error rounded to 3 decimal places, or the string -1 if the target cannot be achieved. Let's look at some examples to understand this better. In the first example, we are given prices 0.700, 2.800, and 4.900, and the target is 8. To meet the target, we round 0.700 up to 1, which gives a rounding error of 0.3. Then, we round 2.800 down to 2, leading to a rounding error of 0.8. Finally, we round 4.900 down to 4, resulting in a rounding error of 0.9. This gives us a total of 1 plus 2 plus 4, which matches the target of 8, and the sum of rounding errors is 1.000. In the second example, the prices are 1.500, 2.500, and 3.500, with a target of 10. Here, the sum of the floor values is 1 plus 2 plus 3, which equals 6, and the sum of the ceiling values is 2 plus 3 plus 4, which equals 9. Since the target of 10 is outside this range, it is impossible to meet the target, and the output is -1. This demonstrates that if the target is not achievable within the bounds of the floor and ceiling sums, we simply return -1. In the third example, the prices are 1.200, 3.400, and 2.500, and the target is 7. Here, we can achieve the target by rounding 1.200 up to 2, which gives a rounding error of 0.8. Then, we round 3.400 down to 3, leading to a rounding error of 0.4. Finally, we round 2.500 up to 3, resulting in a rounding error of 0.5. The total sum of the rounded prices is 2 plus 3 plus 3, which matches the target of 7. The total rounding error is 0.8 plus 0.4 plus 0.5, which equals 0.900. This example highlights how careful selection of floor and ceiling values can help achieve the target with the smallest possible rounding error. Now, let's consider some constraints and edge cases. Each price in the list is represented as a string with exactly 3 decimal places. The target is a non-negative integer, and the sum of the floor values of all prices must be less than or equal to the target, while the sum of the ceiling values must be greater than or equal to the target. If these conditions are not met, we return -1, as it's impossible to achieve the target. For edge cases, if the target falls outside the range defined by the floor and ceiling sums, it's immediately deemed impossible. If the target exactly matches the floor or ceiling sums, no further adjustments are needed. For a single price, we simply round it to either its floor or ceiling to meet the target. Finally, with large inputs, the algorithm must efficiently handle the calculations to ensure it runs within time limits while minimizing the rounding error. To begin solving this problem, let's first consider the brute force approach. The intuition here is straightforward but computationally expensive. For each price, we calculate its floor and ceiling values, which represent the 2 possible ways it can be rounded. Next, we generate all possible combinations of these floor and ceiling values across the prices. For each combination, we calculate both the total sum and the corresponding rounding error. Finally, we check which of these combinations meets the target sum while minimizing the rounding error. While this guarantees the optimal solution because it exhaustively explores all possibilities, the downside is the sheer computational cost. With n prices, there are 2 to the power of n combinations to evaluate, which becomes infeasible for larger inputs, such as when n exceeds 20. This trade-off makes the brute force approach impractical for real-world applications, despite its theoretical guarantee of finding the best solution. Now, a more efficient alternative is the greedy algorithm. The idea here is to reduce the rounding error while ensuring the target sum is met by prioritizing the adjustments that contribute the smallest rounding error. We start by rounding all prices down to their floor values and calculating the initial sum. If this sum is less than the target, we sort the prices based on the difference between their ceiling and floor values, which represents the rounding error of rounding up. Then, we incrementally adjust the sum by rounding up the prices with the smallest rounding errors until the target is reached. This method is significantly faster than brute force, as sorting the prices takes n log n, and the adjustments are linear. However, the greedy approach has its limitations. In certain edge cases, selecting the locally optimal choices can lead to suboptimal global results, which is a common drawback in many greedy algorithms. To address the limitations of both brute force and greedy methods, we consider a backtracking approach with pruning. This combines the exhaustive nature of brute force with the efficiency of pruning to eliminate paths that are unlikely to lead to a solution. Here, we recursively attempt to round each price to its floor or ceiling, maintaining a running sum and a running rounding error. If at any point the running sum exceeds the target or cannot possibly reach the target, we terminate that branch early, which significantly reduces the number of combinations we need to explore. When the target sum is exactly met, we record the result if it has the smallest rounding error so far. While this approach is still exponential in the worst case, the pruning mechanism makes it far more efficient in practice. It guarantees the optimal solution but remains computationally expensive for larger inputs where pruning is less effective. The strategy we ultimately choose builds on the greedy approach but introduces a priority queue to optimize the rounding adjustments. This approach begins by calculating the floor, ceiling, and rounding errors for all prices. Starting with all floor values, we compute the initial sum. If the sum is below the target, we push the rounding errors associated with rounding up into a min heap. The min heap allows us to dynamically manage the prices, ensuring that we always round up the price with the smallest rounding error first. This process continues until the target sum is reached. By using the priority queue, we ensure that adjustments are made in an optimal order, minimizing the overall rounding error. The complexity of this approach is n log n, because inserting into and extracting from the heap are logarithmic operations. This makes it both fast and practical for large inputs, though it is more complex to implement compared to simpler greedy methods. The key insight behind the optimized greedy approach with a priority queue is that minimizing the rounding error requires prioritizing the smallest adjustments. By starting with all floor values, we ensure our initial state is valid and can systematically make adjustments as needed. The use of a priority queue ensures that each adjustment is optimal, avoiding the pitfalls of naive greedy approaches. This strategy strikes the perfect balance between efficiency, simplicity, and correctness. It eliminates the exponential complexity of brute force and backtracking while addressing the edge cases that simpler greedy methods may fail to handle. This makes it the most practical and robust choice for solving the problem, particularly when dealing with real-world input sizes. In this problem, we are tasked with rounding a list of prices, which are floating point numbers, to either their floor or ceiling values. The goal is to ensure that the sum of these rounded prices equals a given target value. However, we also want to minimize the rounding error, which is the sum of the absolute differences between the original prices and their rounded values. To achieve this, we start by identifying the range of possible sums. For each price, we calculate its floor and ceiling values. Then, by summing up all the floor values, we get the minimum possible sum, referred to as min_sum. Similarly, summing up all the ceiling values gives us the maximum possible sum, called max_sum. If the target is outside this range, it means there's no way to meet the target using floor or ceiling rounding, and we can immediately terminate with an error. This ensures that we only proceed with valid cases where a solution is mathematically feasible. Once we know the target is within the valid range, the next step is to calculate the rounding errors for each price. For a given price, we compute the error for rounding it down to its floor and the error for rounding it up to its ceiling. These are calculated as the absolute differences between the original price and its rounded values. To facilitate decision-making, we store this information in a list of tuples. Each tuple contains three key pieces of data: the difference in rounding error between choosing the ceiling and the floor, the index of the price in the original list, and a choice indicator representing whether the floor or ceiling is selected. After calculating these tuples, we prioritize the changes that introduce the smallest additional error. To achieve this, we sort the list of tuples in ascending order based on the error difference. By doing so, we ensure that adjustments to the rounding are made as efficiently as possible, minimizing the overall rounding error. Now that we have prioritized the smallest error adjustments, we can adjust the prices to meet the target. We start with the sum of all floor values, which we call current_sum. The difference between the target and this initial sum is referred to as adjustment_needed. To bridge this gap, we iterate through the sorted list of error tuples. For each tuple, if adjustments are still needed, we round the corresponding price up to its ceiling, reducing the adjustment_needed by 1. This change is reflected in a list called rounding_choices, which tracks whether each price is rounded to its floor or ceiling. If the adjustment is fully completed before we finish processing the tuples, we stop making changes. Finally, with the rounding choices finalized, we calculate the total rounding error. This is done by summing up the absolute differences between the original prices and the values they were rounded to, as indicated by the rounding_choices list. The algorithm then returns the rounded prices and the total rounding error as the solution. The core insights of this algorithm lie in its systematic approach to solving the problem. By validating that the target lies within the range of possible sums, we avoid unnecessary computation and ensure that the problem is solvable. The prioritization of the smallest error differences allows us to incrementally minimize the total rounding error, making the solution optimal. Sorting the error differences ensures that we adjust prices efficiently, focusing on the most impactful changes first. From a data structure perspective, the use of tuples to track error differences, indices, and rounding choices is central to the algorithm's efficiency. Additionally, the rounding_choices list provides a straightforward way to manage and update the rounding decisions. In terms of complexity, the algorithm is efficient, with a time complexity of O(n) log n due to the sorting step, and an additional O(n) for the adjustments, resulting in an overall complexity of O(n) log n. The space complexity is O(n), as we only need to store the error list and the rounding choices. Before applying the algorithm, it is essential to account for potential edge cases. If the target is outside the range defined by min_sum and max_sum, the problem is unsolvable, and we should return an error immediately. Another key edge case occurs when all the prices are already integers. In such scenarios, no rounding is needed, and the solution is trivial. Additionally, when two prices have the same error difference, the algorithm can handle these ties naturally due to the stability of the sorting process, ensuring that any valid choice is acceptable. To better understand the algorithm, let's look at an example. Suppose we have prices 1.2, 2.5, 3.7, and a target of 8. First, we compute the floor and ceiling values for each price. The floors are 1, 2, 3, and the ceilings are 2, 3, 4, resulting in min_sum equals 6 and max_sum equals 9. Since the target lies within this range, we proceed to calculate the rounding errors for each price and store them in tuples for further processing. Continuing with the example, the rounding errors are calculated as follows. For 1.2, the error for choosing the floor is 0.2, for 2.5, it is 0.5, and for 3.7, it is 0.3. These errors are stored in tuples and sorted by the difference in rounding error. The sorted list is 0.2, 0, floor, 0.3, 2, floor, 0.5, 1, floor. Starting with current_sum equals 6, we adjust the first price by rounding it up, resulting in 2, 2, 3, and a new sum of 7. Next, we adjust the second price, leading to 2, 2, 4, and a final sum of 8, which matches the target. The total rounding error is calculated as 1.22 plus 2.52 plus 3.74, which equals 0.8 plus 0.5 plus 0.3, giving a total error of 1.6. The output of the algorithm is the rounded prices, 2, 2, 4, and the total error of 1.6, demonstrating how the method achieves both the target sum and minimal rounding error. Here, we start by importing the necessary modules, floor and ceil from the math library, as well as heap push and heap pop from the heap library, which we'll use for managing a min heap. Inside the minimize error function, we first compute three lists: floors, ceilings, and fractions. The floors list contains the integer part of each price, while the ceilings list contains the next highest integer. The fractions list stores the difference between the original price and its integer floor value, essentially capturing the decimal portion of each price. Next, we calculate the minimum and maximum sums that can be achieved by rounding all prices either down or up. If the target value is outside this range, it's impossible to meet the target, so we immediately return -1. Now, to determine how many prices need to be rounded up to meet the target, we calculate round_up_count by subtracting the min_sum from the target. To minimize the rounding error, we use a min heap to prioritize rounding up the smallest fractional differences, which we build by pushing each fractional value, along with its index, into the heap. We then initialize the total rounding error to 0. To minimize this error, we begin by rounding up the round_up_count smallest fractional values, which we retrieve from the heap using heap pop. For each of these values, the error incurred when rounding up is one fraction, so we add this to the total error. Once we've rounded up the required number of prices, the remaining fractional values in the heap correspond to those prices that we round down. For each of these, the rounding error is simply the fractional value itself, so we add that to the error as well. Finally, we return the total error formatted to 3 decimal places as a string. This ensures the result adheres to the problem's requirements while achieving the smallest possible rounding error to meet the specified target. Here, we begin by importing the necessary libraries and defining the solution class along with the minimize error method. The method takes an array of prices as strings and a target integer. Inside, we initialize 3 arrays, one for floor values, one for ceiling values, and another for the fractional parts of each price. Then, we loop through the prices array, converting each string to a double. Using math.floor and math.ceil, we calculate and store the floor and ceiling values for each price, while also computing the fractional part by subtracting the floor value from the original price. Next, we calculate the minimum and maximum possible sums by adding up the floor and ceiling values across all prices, respectively. These sums represent the boundaries of the achievable target. If the target is outside these bounds, meaning it's less than the minimum sum or greater than the maximum sum, we return -1 since it's impossible to meet the target under these constraints. If the target is within the achievable range, we proceed to calculate how many values need to be rounded up in order to meet the target. This is determined by subtracting the minimum sum from the target. To handle the rounding process efficiently, we use a priority queue, or min heap, to store the fractional parts. The heap ensures that we can access the smallest fractional values quickly, which helps minimize the rounding error. We initialize the total rounding error to 0, then iterate for the number of values that need to be rounded up. In each iteration, we pull the smallest fractional value from the heap, add the rounding error incurred by rounding it up, which is 1 minus the fractional value, and update the total error. After rounding up the necessary values, we add any remaining fractional parts from the heap directly to the error, as these will be rounded down. Finally, we format the total error to 3 decimal places and return it as a string. The method concludes with the closing braces for both the minimize error method and the solution class. At this point, we've fully implemented the solution. The algorithm is designed to handle the rounding process in a way that minimizes the total error, using the priority queue to ensure that the smallest fractions are rounded up first. This approach balances computational efficiency with accuracy, providing a formatted result that satisfies the problem's constraints. In this example, we start with the input prices as strings and the target value of 8. The first step is to process the prices. We convert each price to a float, then calculate 3 key lists: floors, ceilings, and fractional parts. The floors represent the integer portion of each price, giving us 0, 2, 4. The ceilings are the next integers above the prices, resulting in 1, 3, 5. Finally, the fractional parts, which represent how far each price is from its floor value, are 0.7, 0.8, 0.9. Next, we calculate the minimum and maximum sums by adding up the floors and ceilings, respectively. The minimum sum is 6, and the maximum sum is 9. Since the target value of 8 is within this range, it's possible to achieve the target by rounding the prices. To determine how many prices must be rounded up, we calculate the difference between the target and the minimum sum, which is 8 minus 6, giving us a rounding count of 2. This means we need to round up 2 of the prices to meet the target. To minimize the rounding error while rounding up 2 prices, we focus on the fractional parts. We use a min-heap to efficiently track and process the smallest fractions first, as these will contribute the least error when rounded up. The heap is initialized with tuples of the fractional values and their indices, resulting in 0.7, 0, 0.8, 1, 0.9, 2. Next, we begin rounding up the smallest fractions. First, we pop the smallest fraction, 0.7, from the heap and calculate the additional error caused by rounding it up, which is 1 minus 0.7, or 0.3. We add this to our total error, making it 0.3. The heap now contains 0.8, 1, 0.9, 2. We repeat this process for the next smallest fraction, 0.8. Rounding it up adds 1 minus 0.8, or 0.2, to the error, resulting in a total error of 0.5. The heap is now left with 0.92. Finally, we add the remaining fractions to the error without rounding them up. The remaining fraction, 0.9, is added directly to the error, bringing the final total error to 1.4. The result is then formatted and returned as the string 1.400. In our second example, we examine a case where meeting the target is impossible. The input prices are 1.500, 2.500, 3.500, and the target is 10. After processing the prices, we calculate the floors as 1, 2, 3, the ceilings as 2, 3, 4, and the fractional parts as 0.5, 0.5, 0.5. The minimum sum of the floors is 6, and the maximum sum of the ceilings is 9. Since the target value of 10 exceeds the maximum possible sum, it is impossible to achieve the target by rounding the prices. In such cases, we immediately return -1 to indicate that the target is out of range. Additionally, this demonstrates the importance of checking the target's feasibility early in the process to save computation time. Moving to the next part, we consider an edge case where no rounding is required. In this edge case, the input prices are 1.000, 2.000, 3.000, and the target is 6. Here, the prices are already integers, so the floors and ceilings are identical, 1, 2, 3, as a result, the fractional parts are all zeros, 0.0, 0.0, 0.0. The minimum sum and maximum sum, both equal to 6, indicate that the target matches the sum of the unrounded prices. Since no rounding is necessary, the rounding count is calculated as 6 minus 6, which equals 0. We then add up the remaining fractional parts, which are all zeros, resulting in a total rounding error of 0.0. The result is formatted as the string 0.000 and returned. This example highlights the efficiency of the approach in handling cases where no adjustments are needed, ensuring the solution remains optimal and straightforward in such scenarios. To analyze the time complexity of this solution, we start with parsing and pre-computing values. Here, we iterate over the list of prices to compute the floor, ceiling, and fractional part for each price. Since these calculations are done in constant time for each price, and there are n prices, this step takes n time. Next, we calculate the sums of the floors and ceilings using Python's built-in sum function, which also iterates through the list of size n and thus requires n time. Finally, we build a min-heap from the fractional parts. Each insertion into the heap takes log k, where k is the current size of the heap. Since we perform n insertions, this step contributes n asterisk log n to the time complexity. Together, these steps set the stage for the subsequent heap processing. Processing the heap is the next major component of the solution. Here, we perform round_up_count extractions from the heap. Each extraction operation takes log n, and in the worst-case scenario, round_up_count could be equal to n, meaning all elements require rounding up. This makes the time complexity of this step n asterisk log n. Additionally, if round_up_count is less than n, we still need to handle the remaining elements in the heap. Extracting these remaining elements also takes n asterisk log n. Combining these, the overall time complexity of the solution is dominated by the heap operations, resulting in O n asterisk log n. This demonstrates how the use of a greedy strategy with a heap ensures efficiency while meeting the problem's constraints. Now, let's consider the space complexity of the solution. First, we store the pre-computed lists for floors, ceilings, and fractional parts, each of which contains n elements. This requires O n space. Next, we use a min heap to manage the fractional parts during the rounding process. The heap can store up to n elements at any given time, which also requires O n space. Finally, we have auxiliary variables such as min_sum, max_sum, round_up_count, and error, all of which use constant space, or O1. When we combine these factors, the overall space complexity is O n, driven primarily by the storage for the pre-computed lists and the heap. When comparing this optimized approach to a naive solution, the efficiency of using a heap becomes clear. In a brute force approach, we would need to explore every possible combination of rounding up or down for each price to achieve the target. This results in 2 to the power of n combinations, leading to an exponential time complexity of O 2 to the power of n. Space complexity would still be O n for storing intermediate states. In contrast, the optimized solution reduces the time complexity to O n asterisk log n by leveraging a greedy approach with a min heap. This dramatic improvement makes the solution scalable for larger inputs. Moreover, the space complexity remains O n, which is the minimum required to handle the input and heap operations effectively. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, where the target equals min_sum, no rounding up is needed, and heap operations are minimal. Here, the time complexity is O n. In the average case, some rounding up is typically required, making the time complexity O n asterisk log n, as heap operations dominate the runtime. In the worst case, when round_up_count is close to n, all elements require rounding up, and the time complexity remains O n asterisk log n. Mathematically, the solution's complexity is derived from parsing and pre-computing, which is O n, and heap operations for insertions and extractions, which dominate at O n asterisk log n. Therefore, the overall time complexity is O n asterisk log n, while the space complexity stays at O n, making this solution both efficient and practical for real-world use cases. When tackling this problem, there are a few common mistakes to watch out for. First, overlooking edge cases can be a major pitfall. For example, if all the prices in the input are integers or if the target sum matches the sum of the floor values, the solution might become simpler, but these scenarios need explicit handling. Missing these cases could lead to either unnecessary computations or incorrect results. Another issue arises from rounding errors in floating point arithmetic. Since floating point numbers are stored with inherent inaccuracies, directly comparing their sums can lead to precision problems. A good way to avoid this is by relying on integer arithmetic whenever possible, such as scaling values, or by carefully accounting for precision. Additionally, some solutions fail to consider all valid combinations of floor and ceiling values, particularly in brute force approaches. This omission can result in missed solutions or an incomplete search space. Lastly, improper handling of sorting or priority queues in greedy methods can lead to inefficiencies, such as sorting the entire list repeatedly. Optimizing the sorting process or maintaining a structured heap for updates can make the algorithm more efficient. Another frequent mistake is assuming the problem always has a unique solution. In reality, there can be multiple valid configurations that meet the target, and failing to account for this can result in suboptimal or incomplete outputs. To avoid this, it's important to verify all valid solutions. Now, let's talk about how to approach this type of problem in an interview setting. Start by breaking it down into the trade-offs between brute force, greedy, and optimized methods. While brute force ensures correctness, it's computationally expensive, especially for larger inputs. Greedy approaches, on the other hand, reduce the search space by targeting the smallest fractional parts. A key insight here is to recognize that rounding problems often revolve around minimizing absolute differences, which can steer you toward a greedy or dynamic programming solution. Additionally, interviewers appreciate when you can show progress in optimization, like reducing complexity from exponential to something more manageable, such as O n log n. It's also crucial to communicate the trade-offs clearly. For instance, brute force might be acceptable for small constraints, whereas optimizations become necessary for larger ones. This problem also shares similarities with several related LeetCode problems, which can help strengthen your understanding. For example, LeetCode 2801, Count Stepping Numbers in Range, involves exploring combinations systematically. LeetCode 1278, Palindrome Partitioning 3, and LeetCode 198, House Robber, demonstrate the use of dynamic programming or greedy techniques. Additionally, LeetCode 875, Cocoa Eating Bananas, showcases how binary search can be combined with greedy strategies. Now, considering alternative approaches, brute force is the most straightforward, as it explores all combinations of floor and ceiling values. While this ensures correctness, the exponential time complexity, 2 to the power of n, makes it impractical for larger inputs. A greedy approach minimizes rounding error by focusing on numbers with the smallest fractional parts, achieving a more efficient n log n runtime due to sorting. Dynamic programming can also be used to explore rounding combinations systematically, which is great for handling larger constraints, though it may demand more space. Finally, binary search can sometimes be applied to efficiently pinpoint the optimal rounding threshold. Each of these approaches has its strengths, so the choice depends on the specific constraints and requirements of the problem you're solving. Great job! To recap, we tackled the minimize rounding error to meet target problem, focusing on precision and algorithmic trade-offs. I hope you found this session insightful. Be sure to practice and explore similar problems to strengthen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!